Hello again, students. Here with an overview of binomial and geometric, and so I'm going to go through this. This is actually a note sheet with some examples on it. So I'll go through mainly the notes part, but I'll get a little bit into the examples just to show how the calculations take place here. So starting with the binomial, this binomial formula right here, along um, with the with the mean and standard deviation formula, those are all on your formula sheet. And so I'll talk about each one of those and what the values mean, and then we'll see it in action a little bit here. So this formula right here, first of all, the probability that x equals k, what that is referring to is the notion of having a random variable x with a certain number of successes. So for instance, made free throws. Um, so this might be out of 10 free throws, what is the probability that you make 7 of them? So that would be the probability then that x equals 7. Now, the values themselves here, n is the number of trials and k is the number of successes. So that would, in this case, that would look like this. Now, bear in mind that this is not division that's taking place. A lot of times students will put a fraction bar in between the n and the k with the idea that this is a division 10 divided by 7. This is 10 choose 7. And 10 choose 7 is outlined in this formula right here. This is a combinatorics formula that really is looking at the idea of if you take 10 shots and you make 7 of them, this is all the orderings that you could have for the makes and misses. For instance, you could make the first 7, then miss the last 3. Or you could make the first 6, then miss 1, then make 1, then miss 2. Or you could miss the first 3 and make the next 7. Or you could miss the first, 5th, and 8th shots. All these different arrangements of successes and fails. Um, that gives you the orderings there. And you can find this function on your calculator. It's under math probability. NCR is what it looks like. So you actually have to type a value in first. You'd type in 10, and then you'd go to the NCR function, then you'd put in 7. So there's actually 120 different orders that you could make 7 shots and then miss 3. So that value there, this really is a value of 120 right there. Now these here, this represents the probability of a success. That's what P would be. So if you are a 75% free throw shooter, for instance, then that would be 0.75. And the K again is the number of successes. So if we were to make 7 shots, that would be a 7 there. 1 minus P then naturally is the chance of a fail, which would be 25% in this case. And then the N minus K would just be how many fails. Okay, so the way you would read this is essentially trials choose successes, chance of a success to the number of successes, chance of a fail to the number of fails. And again, that formula is on your formula sheet. Now, what defines a binomial is really actually what's perhaps more important, and that's what you're seeing right here with these 4 options right here. The one that stands out in the bold there is what really, in an AP exam question, for instance, is going to be probably your biggest indicator that this is a binomial. And the idea is with that fixed number of observations is that it's not going until we have a certain number of successes or a certain number of fails. This is truly 10 tries at something, or you picked 3 families. What are the chances that exactly 2 of them have a dog? You pick 25 iPhones. What are the chances that 10 or less of them have a defect or whatever it happens to be? So it starts off with that fixed number of observations. So this is the key, and this is actually one of the big differences here, the big difference between a binomial and a geometric, which is the second half of this. This here, just success or fail, just means it's a binary outcome. Again, it's all relative. Success could be making a shot, or it could be a death or something that's, so it's not in the straight tone of the word. It's just meaning that we define something as what we're counting as a success, and then the other is a fail. The observations being independent is important. Okay, so that independence idea, it's just saying that each free throw is not affecting the next, or each iPhone is not affecting the next, or each family is not affecting the next, whatever it happens to be. And then with that independence, comes number 4, the idea that the probability of a success will never change within that situation or in that scenario. So the probability of us making a free throw is, if it's 75%, that remains the probability of a success or of a made free throw throughout. So this is what defines it. Again, what you're looking for in questions are things really related to that fixed n, with the question being, out of this many tries or out of this many picks or whatever it is, what are the chances of exactly this many successes? Or it could be a more or less question, which we'll get to shortly. The calculations of mean and standard deviation or variance, as you can see, mean is just n times p. So on average for 10 free throws, if we're a 75% free throw shooter, we're just saying we would expect to make on average 7.5 free throws. Standard deviation, again, variance and standard deviation are the same thing except for the radical. Okay, so variance is standard deviation squared. So what we would see here is 10 free throws, 0.75, 0.25, and we'd calculate that, and that would be our standard deviation. Now keep in mind this is a sigma, okay? So mu and sigma, again, a lot of times end up on that z path down the road, okay? So do keep that in mind, that a part B sort of question could be using a normal distribution here in the long run. But this now 1.37 just means that on average, a player would make 7.5 free throws out of 10, give or take about 1.37 on average as a standard deviation, assuming 10 free throws and a 75% chance of success. So that's a little breakdown. I apologize, ran out of room up here, but that would be 0.25 to the 3. Never wrote that up there. Okay, so let's just look at this scenario here quickly, just to talk about what it looks like in formula and to talk a little bit about the shortcuts that we can use with the calculator. So the scenario here, assume every time you're crossing 7 at the 7 and 101 stoplight is independent, and that you have a probability of 0.36 or 36% of hitting a green light. So you consider 5 trials. So what we could do here then is, for instance, this right here would be the probability that x equals 0. Again, we have 5 trials, and this is talking about 0 successes. These two numbers will always be the same. The chance of a success was 0.36, and we had 0 of them. The chance of a fail is 0.64, and we had 5 of them. And then to find that, you could do this calculation, but you're probably going to do a calculation on your calculator that is a binomial PDF. Okay, binomial PDF. So that's under second vars, okay, or distributions. So you go second vars, hit the up arrow is probably easiest. That gets you to the binomial PDF most quickly, and it's going to be NPX. Depends what operating system you have in terms of, if you have the newer operating system, it will ask you trials first, which for us would be 5. So N is 5, P is 0.36 in this case, and the X value we're looking at is 0 successes. And so you can do that, and that gives you, of course, we would round here, but this would be about 0.1074. So there's about a 10 or 11% chance that we would get 5 straight trips where we did not hit a green light at that stoplight. And then from there, we can just change each of these. This gets to be busy work if we write them all out, but we could change this to 5 choose 1, and then this would be 1, and this would be 4 instead. Okay, and this would be the next one then. All right, on your calculator, if you just hit second enter, it will bring back up our last formula, and you just change the 0 to 1 when you arrow back there, and you can get that next probability. So there is about a 30.2% chance that we'll hit exactly 1 green light. And we could keep doing that and change that to 2 and so on, all the way up to the 5th one. And I won't write them all out, but the 5th one here would be about 0.0060. So obviously a very small chance that we'd hit 5 straight green lights at that stoplight. Now, what this does is you probably won't create the table every time. And so you just have to think about the questions that could be asked with this. So I could ask a question, or the AP exam or whoever could ask a question, simply a probability that x equals. okay? And in that case, you would just PDF and we'd move on like that. The other scenarios are you could get a less than or a less than or equal to, okay, scenario. So for instance, less than 2 would just be the 1 and the 0. Okay, so this is where it's nice to at least write out the top part of the chart. And if you just write this out, then that helps you kind of organize what this would be. So for instance, less than 2, we can see that it's that. If it's greater than, greater than or equal to 3, then we see, okay, greater than or equal to 3, this would be here and up. So we'd have to add up those 3. The last situation is it could be something like 2 is less than x, which is less than or equal to 4. Okay, so in this case, 2, so it's got to be greater than 2, so that would start at 3, okay, and then it's less than or equal to 4, so that would include 4, so that would actually be 3 and 4 exactly. So to think about all these scenarios, make sure that you organize. It's very easy in a situation like this to see a student accidentally include 2 in there, like on that last one here, when 2 is not supposed to be included. So you got to make sure that you're setting that up properly. And the one other piece with the calculator here is the calculator has a second function called binomial CDF, which stands for a cumulative distribution function. And what a cumulative distribution function is going to do is find the probabilities from 0 counting up. So for instance, this one here, less than 2, we wanted 0 and 1. We could answer that as the binomial CDF 5.361, and that would actually get the 0 and the 1 for us. Okay, so that would be the less than 2 scenario. The greater than or equal to 3 scenario here, that one's a little different because, again, greater than or equal to 3, so we want 3, 4, and 5. Well, the CDF starts at 0. So in this case, you could actually do a 1 minus binomial CDF, 5.36 and 2, because then that would take out 2, 1, and 0, which leaves us with 3, 4, and 5. Okay. The other way you could do that is simply PDF of 3, PDF of 4, and PDF of 5 and add them all up as well. The last one here, really quickly with the CDF and 2 and greater than 2 but less than or equal to 4, what you do here is you actually CDF 4 or less. Okay, so that would give us 4, 3, 2, 1, and 0. But we don't want all of those because we need to only keep 3 and 4. So we actually would get rid of 2 or less. So we'd subtract from that a binomial CDF 5.362. And you'll see that on the next slide. There's questions like all of these in the practice problems here. So you'll get a chance to see each of those, but keep in mind the CDF works from 0 up, and you just really want to make sure that you're subtracting the right amount. As you'd expect, most commonly, this is the concern if students accidentally put a 3 in there or a 1 in there, and you just have to be careful that you're getting rid of exactly what we need to get rid of there. Okay. So here, this part, the top part of this has some scenarios that you're just checking for the binomial, and then there's some calculations, and you can see there's a couple equals, there's the less than or equal to, there's the greater than, there's the in between. The answer key for that is also in Schoology as well. But just as you're looking at this, flipping a coin 10 times and let x be the number of heads, that's again fixed number of trials, the coin flips are independent and so forth. Rolling a die 20 times, and x the number of times a 4 is rolled. Again, we have success, fail, they're independent, there's a fixed number of trials. But it's things like this, flipping a coin and let x be the number of flips to get 4 heads. Well, that's an indefinite number of trials, so that would not be a binomial. Without replacement, that shows a lack of independence, so that would not be a binomial. Again, without replacement here is an issue, but what is the case here is we do have 10 computer chips out of 10,000. So this actually comes back a little bit to this 10n is less than capital N that we've talked about periodically, that we're taking a very small portion of the population. So we would actually, in like a normal distribution in a Z problem with a normal curve, we would let this fly. But by the true sense of the word here, as long as there's not replacement, then technically it's not the perfect independence for a binomial, but we would be able to estimate in this case using a normal distribution and get a pretty similar answer, which I do in this packet on the next slide here. So 5 technically no, because it's not independent by the letter of the law, but we took such a small portion of the population, namely 10 out of 10,000, so you could estimate it with the normal. So here's a situation here where I have a question where we look at the mean and the standard deviation. This is using the binomial, so that would be a CDF with 100 questions. There's 4 options, so if we're guessing, there's a 25% chance we guess right, and this would be 20, and that would be one way of finding it. The other way of finding it would be using normal distribution to estimate, and so we would have here the x would be 20, and then we'd use the mu and the sigma to calculate there. Is the normal distribution a good approximation here for the binomial? Well, did we have a random sample? Did we take less than 10% of the population? So did we get 10n is less than capital N to help verify for us that independence? And so we look at those pieces and make sure that we followed enough proper rules here in terms of sample size with respect to population size to actually move forward in that sense to get that independence. We'll leave it at that for the binomial and quickly here on the distinction of the differences with the geometric. So geometric, very similar to binomial in the sense that there's a success and a fail. The trials are independent. The probability of a success does not change. But what ends up happening is in this case, we just go until we get a success, whatever is defined as a success here. So this formula here is just essentially set up so it's the number of fails to the number of tries minus 1. So for instance, let's say we're flipping a coin, or let's say we're rolling a die, and we just want to figure out the probability that it takes us exactly 10 tries to roll a 6. That would mean that we'd have the chance of a fail to the number of fails times the chance of a success. Okay, so that's just naturally there's 5 sides of a die that aren't the number 6, and we had 9 of those happen, and then we had that success. If we were shooting a free throw and we wanted to see what's the chance using that same free throw example, what are the chances it took us 4 tries? So again, keep in mind X was successes on the binomial. Now it's really tries on this one, or attempts. So for the free throw, this would mean that if we made our first free throw on our 4th try, that would mean we'd have 3 misses at the 25% chance of a miss, and then the 0.75 would be the make. So you're really just actually thinking along the line. So you say it's a miss, so it's a 0.25. It's another miss, so it's another 0.25. It's another miss, so it's another 0.25. And then finally we get our 0.75. So it's like you're replacing fail over and over and over again with that probability, and then you end with 1 probability of the success. This is just a shortcut. So if it asked a question, for instance, what are the chances it would take us more than 10 flips of a coin to get a number 6, then we just take the chance of a fail to that number. The reason this shortcut can be helpful is because naturally when it's an indefinite number, it could take us 11 tries, could take us 12, 13, 14, 15, 16, so on. And so all of those scenarios would be endless to add them all up. So you just look at everything else, and this would be just that we started with 10 fails, and then that leaves every success opportunity down the road. So if we were to create a table in that situation, sorry, there wouldn't be a 0 there because we'd have to have a trial to get a success, but we'd create a table, and we could do this where this is number of tries to get our success. We could calculate all of those, but keep in mind this table goes on forever. And to get more than 10, we'd just be looking at 1 minus the table from 10 or less. And so if I move this over and put a 10 here, we'd be looking at everything else if it was more than 10. So you're really just kind of finding those 10 and taking 1 minus that, because it's still 100% chance over an infinite number of trials that we will have that success. We just aren't going to calculate all of those individually. Okay, the mean and the standard deviation formula, you can see these are on the formula sheet. Just 1 over p for mean. So for the rolling a 6 on average, it would be 1 over 1/6. There's 6 rolls on average to roll a 6. Standard deviation, you can see root of 1 minus p over p. And so again, we just have root of 5/6 over 1/6 there. And that would again be a mu and a sigma. So those could be used again in the long run for a z situation potentially. We won't get into the scenarios in which that would be here, but the calculation then for geometrics, you get these sorts of questions. Define a success. What's the random variable of x? And the random variable x of interest would be the number of tries to get that success here. So it might be the number of flips of the roll of a die to get the 6. It could be the number of free throws to make one, so forth. And then we have a mean question, and then again, third try, buyer, third try, and so forth. And just to end it here, just a heads up that there is a geometric PDF and a geometric CDF on our calculator again. And the CDF, the PDF first, these are both second vars again. And the geometric works a little differently in that we don't have that fixed number of trials. So we just would put the probability of a success and then the number of tries. So again, for the free throw problem, we have a 75% chance of making our free throw. What are the chances it takes us 4 tries exactly to make that free throw? Would be this is a 0.0117, which again is just geometric PDF 0.75, 4. Now the CDF again is going to be that many trials down to 1, okay, not down to 0 because it's not successes here, it's tries. So in this case, if I did a geometric CDF of 0.754, that would instead be determining what are the chances that I make my first free throw by my 4th shot, rather than on my 4th shot, just by my 4th shot. As you can imagine, that's a much higher probability. It's about a 99.61 probability there. Sorry, I'll go backward here. And that's to be expected if you're a 75% free throw shooter. You really expect to make at least 1 in your first 4 shots there. Now, this geometric CDF can work hand in hand with the shortcut. Again, the other way to do this is 1 minus the geometric CDF, which in this case would be 1/6, 10. Okay, and so the geometric CDF of 1/6, 10 would be showing you what are the chances you roll a 6 within your first 10 tries. So 1 minus that would be anything more than 10 tries. Okay, so that would give you the same answer as 5/6 to the 10th would in this situation. We'll leave it at that. If this leads to any other questions, please let me know. Thank you for listening.